What's going on, y'all? In this video, we're going to look at an algorithm to transform an n-digit decimal representation of an unsigned integer into the corresponding m-bit binary representation. This is the first of two algorithms to achieve this decimal to binary conversion. Not only do we successfully want to transform our n-digit decimal number into the corresponding m-bit binary representation, we want to do so using a specific strategy. The algorithm we develop in this video is going to start with bit b sub m minus 1. We're going to see this called the most significant bit in our binary representation. And then we're going to work down through the other bits step by step. So in the second step of the algorithm, we're going to move down to the b sub m minus 2. And we're going to keep going all the way down till we get to the last bit, b sub 0. That is when our algorithm will end. We call that last bit the least significant bit in our representation. Let's get a little bit more precise with our notation. Remember back to the general form for an binary representation of an unsigned integer. If we have that unsigned integer y in the set Blackboard U, the set of unsigned non-negative integers, the binary representation for y is given by m binary digits, or m bits. The leading bit, the one with the highest power, is the first one in our representation, and that's labeled b sub m minus 1. Remember, the index value, or the subscript, matches identically the power on base 2 that coefficient is matched with in our summation representation. We move down to the second most significant bit, b sub m minus 2, which get matched to 2 to the m minus 2. We continue all the way down to the least significant bit, b0. That bit gets matched with 2 to the 0. We said that each of those binary digits was in the set of binary digits, so it either could be a 0 or 1. And then the notation we are introducing here is b sub m minus 1 is the most significant bit, while b sub 0 is the least significant bit. And this idea of most significant and least significant has to do with what happens when we make errors. Imagine that this number represented money in your bank, and then ask yourself which would be most significant if your banker made a mistake. Would you care most that they make sure to track the highest power of 2? Or would you care most that they make sure to track the least power of 2? Well, if you enjoy having money in your bank account, you would say it is most important for them to match the most significant bit. In other words, it is most significant that we get this correct, because the power of 2 is much higher on that bit. We'll see more of that notation as this class goes on, but remember, the most significant bit is the one associated with the highest power of our base, and the least significant bit is the one associated with the least power on our base. Using that general form as a foundation, we're going to create something known as a value box or value table that matches each power of 2 with the corresponding bit. This will be super helpful as we develop our algorithm. So remember that the position number identifies both the bit number, or the index on the bit, as well as the power matched with that bit. When we create a value box, we simply have two rows where each bit is matched identically with its power of 2. In the algorithm we're going to develop in this video, we're going to actually generate or create the most significant bit first, the one with the highest power of 2, and then we're going to step down this table step by step until we reach the least significant bit, and then we'll say that our algorithm is over. Like all good computer scientists, we're going to start our analysis using paper and pencil, and this value box will be a super useful tool to get a sense of how our algorithm works, so that we have a very, very well-refined strategy before we write a single line of code. That is a major theme in numerical analysis. Really spend time understanding the problem, and then find the syntax that best implements the approach that we take on pen and paper. In honor of that approach of really trying to understand what we're doing when we're converting from decimal to binary, let's start with example 1. We have the unsigned integer y1 equal to 27 base 10. And we immediately ask ourselves, how do we convert 27 in base 10 representation into the corresponding binary representation? One of the first questions we ask ourselves is, how many binary digits are we going to need to encode 27 as a binary number? And we remember from a previous video that we can answer this question by identifying the powers of 2 that sit on the left and right-hand side of this decimal representation. In this situation, we know that 27 is bounded below by 16 and bounded above by 32. When we write that using powers, we know that 2 to the 4th is less than or equal to 27, which is strictly less than 2 to the 5th. By applying log base 2 across this entire chain of inequality and doing a little bit of math involving floor functions, we know that the number of binary digits, the number of bits needed to encode the number 27, is given by the floor of log base 2 of 27 plus 1, which is 5. If you need a reminder of where this formula came from, please go back and watch that other video because we cover this formula in that video with glorious detail. Once we have that information that the number y1 equal to 27 in base 10 representation can be represented using a string of binary digits, bits, b4, b3, b2, b1, b0, 5 binary digits, where the most significant bit has index 4 representing the highest power of 2 to the 4 less than 27. Now what we want to do is break 27 into the appropriate powers of 2. And the first question that we ask ourselves is, what is the highest power of 2 that is less than 27? This is where we go into the Rolodex of our memory or into our wallet where we keep a table of powers of 2. Notice that 2 to the 4th, which is 16, is the highest power of 2 that's less than 27. We also recognize that based on the fact that we're going to have 5 bits, the highest power is 2 to the 4th. The moment that we know that 16 is less than 27, we can decompose the number 27 into a pure power of 2, in other words, 2 to the 4th, plus some extra information that is a sum of less significant bits. The moment that we have that, we know that there's going to be a 1 in B4 because I have one group of 2 to the 4. And I have this extra remaining information, but I can ask myself here, what is the next highest power of 2 that is contained in the extra information between 27 and 16? Well, that extra information is 11. Let's run through the powers of 2. What's the highest power of 2 less than 11? Well, it must be 2 to the 3rd, which is 8. So now we can decompose 11 into 2 to the 3rd plus 3. The moment that I've done that, I've now gotten that my B3 bit will also be 1 because not only do I have a factor of 2 to the 4, but I also have a factor of 2 to the 3, and I now have a new bit of extra information, which is 3. So the next question that I ask is, what is the highest power of 2 that is less than 3? That must be 2 to the 1st. And now all of a sudden, I have 27 written as a linear combination of powers of 2. Which powers of 2 did I use? Well, we knew that in the first step, I had 2 to the 4. So that first situation, I pulled off the most significant bit. I have one of those. Then when I had the extra information, I looked for the next highest power of 2. Next highest power of 2 was 2 to the 3rd. So here in my value box, I know that I have 1, 2 to the 3rd. When I looked at the extra information in the difference between 27 minus 16 minus 8, that extra information was 3. 3 is less than 4, so I know I have no need for 2 squared information. There is no value of 4 in that linear combination. 3 can be decomposed into 2 powers of 2. That's 2 to the 1st and 2 to the 0. So I actually have need for 2 to the 1st in my representation and also 2 to the 0. Notice that value box gives me a very, very quick way to associate which powers of 2 show up in my linear combination or my binary representation of my decimal number. It's worth reinforcing that this algorithm started with the most significant bit and then worked its way down step by step until we reached the least significant bit, which was the remainder how many ones did we have in our representation. As promised, this value box is a heuristic. It's a tool we can use to solve problems that immediately translates our power representation into a binary representation, and that's exactly what we've done here. 27 base 10 is equal to 11011 base 2. These representations encode the same value underneath. Since we're developing our algorithm and we want to make sure that our thinking or approach is legit, it's worth the extra second to confirm that the calculations that we just did actually correspond with what we would expect. Let's go ahead and boot up MATLAB and take des2bin of 27. The moment we do that, we see that the binary representation of 27 that MATLAB is reporting is 11011. That's the same thing that our algorithm just produced. Good news. Let's refine our thinking for this algorithm a little bit more by analyzing a slightly more complex example and seeing what we can learn about our approach from this example. In this case, what we'll do is we'll look at the number 149 in base 10, and we'll ask ourselves, can we convert 149 into binary? Remember, we're going to start with this question, how many binary digits, how many bits do we need to encode that number? In order to answer that question, we position that number between two pure powers of 2. In this situation, we see that 149 is between 128 and 256. In power notation, that means 149 is kind of wedged between 2 to the 7th and 2 to the 8th. And we remember from our previous video that all integers that are greater than or equal to 2 to the 7th and strictly less than 2 to the 8th can be encapsulated using 8 binary digits. That is exactly what this formula tells us. We now immediately know that 149 is going to be written as an 8-bit binary integer. The leading position for that binary number is 7, one less than the number of bits. And thus we have insights for the first step in our algorithm. Remember, we asked ourselves, find the highest power of 2 that is less than 149. We can reference our table or our memory, or we can use the fact that this is 8 to say that that probably should be 2 to the 7th. 2 to the 7th is 128. So what we'll do is we'll decompose 149 as a sum, 128 plus some extra information. Well, we know the extra information, 149 minus 128 is going to be 21. Now the question is, what is the highest power of 2 less than this extra information? Well, let's go ahead and just kind of scroll down. Is it 2 to the 6th? No. 2 to the 5th? No. 2 to the 4th? Yes. We're going to now decompose 21 into 2 to the 4th plus 5, where 5 is the difference between 21 and 2 to the 4th. Now we ask ourselves, what's the next highest power of 2 that is less than 5? It's not 2 to the 3rd, must be 2 squared, so we can decompose 5 into 4 plus 1. But the moment that we have this representation, we actually can rewrite that using power notation. Specifically, we see that 149 is 2 to the 7th, which was the first power I picked off. I then looked for the next highest power that was in the remainder, which was 2 to the 4th. Then I looked for the next one, which was 2 squared. Then the last one was 2 to the 0. In other words, this algorithm identified first that I have one group of 2 to the 7th, no groups of 2 to the 6th, no groups of 2 to the 5, one group of 2 to the 4th, 0 of 2 to the 3rd, 1 of 2 squared, 0 of 2 to the 1st, and 1 of 2 to the 0. Notice that we indeed started with our most significant bit, worked our way down to the least significant bit, and then got our final binary representation using that combination of decomposing 149 in terms of the highest powers of 2 plus some extra information. Each next step took away the next highest power of 2 from the extra information until we got down to 2 to the 0. We can then read the binary representation immediately from this value box. 149 base 10 is 1001, 0101. Let's do one last example, which is by far the most complex that we've looked at so far. We'll use this to convince ourselves that we really understand what we're doing and to craft a more general approach, an algorithm, a program that implements this strategy for any input that we desire. From that standpoint, we'll start with the unsigned decimal integer 19229, that's in base 10 representation. And then we'll ask ourselves a famous question, how many bits are necessary to encode that number? Remember, that's identical to asking the question, what are powers of 2 to the left and right of that number? Well, let's go ahead and search our Rolodex of powers of 2. If we start from 2 to the 16th, 65536, that is definitely not less than 19229, so it's not that one. We'll move one up. Nope, that doesn't work. If we go to 2 to the 14th, notice 2 to the 14th, which is 16384, is indeed less than or equal to 19229. And then that's strictly less than 2 to the 15th. We can write that in power notation, which immediately leads us to the formula that in order to encode 19229 in binary, we're going to need 15 bits, which is given by floor of log base 2 of 19229 plus 1. Thus, we begin our search knowing that we're looking for 15 bits, the leading power of which is going to be associated with 2 to the 14th. Now we want to find the highest power of 2 that is less than our original number. We already know that that's going to be 2 to the 14th, which from our table is 16384. And then there's some remaining information. So I take 16384 away from my original number, and then I have this remaining. I'm going to ask myself the next question. What is the highest power of 2 that is less than that number? I can already tell you that that's going to be 11. So 2 to the 11th is 2048. Now I look at that number and decompose it into two components. One is 2 to the 11th. The other component is going to be the extra information, 2845 minus 2 to the 11th, which is 797. Then I ask myself, what power of 2 is less than 797? Well, I can go all the way to 2 to the 9th and decompose 797 into 2 to the 9th plus 285. Do you notice that in each step, I'm kind of stepping down piece by piece? Or may I say, repeating this process one step at a time for a finite number of times? This is where I need a beard and a pipe. Do we have a programming structure that allows us to repeat a step a finite number of times? Wherefore art thou, loops? All right, so here we go. We now have this extra information, which is 285. We're going to ask ourselves the question, what is the highest power of 2 that is less than 285? Of course, that must be 256. So we decompose 285 into power of 2, which is 2 to the 8th plus 29. Well, 29 is actually not so bad. We know 29 is going to be 16 plus 8 plus 4 plus 1. Please do those steps for yourself. I was running out of room on this paper, and so I decided to be lazy. The moment that we have that decomposition of the number of 29, we can now write our original number in terms of its power of 2s. Notice this linear combination is one group of 2 to the 14th, a group of 2 to the 11th, 2 to the 9th, 2 to the 8th, 4, 3, 2, 0. Now the trick is just to identify which powers of 2 show up in this linear combination. We know that one power of 2 to the 14th shows up, none of 2 to the 13th to 2 to the 12th, and then literally everywhere where one of these powers shows up in this sum, a 1 is going to be placed in the appropriate space in the value box. All powers that do not show up are going to have zeros, which leads to our binary representation given by this 15-bit string of binary digits, which is actually our binary representation of this decimal number. Moreover, we're seeing that this general approach proceeds step by step down from the powers of 2, starting with the highest power of 2 that is less than our number, and then literally asks, is the next power of 2 down less than the remainder? If so, capture that information. If not, skip it, and then go down, repeat, repeat, repeat. In other words, this is a perfect place to use a for loop. For loops are designed to allow us to repeat the same operation for a set number of times. So now we have the intuition. Let's use a for loop to program this algorithm into a general approach to turn any decimal number into its binary representation. Let's do a little bit of analysis on this example to see if we can get our head around how to describe that algorithm in English. The first question that we ask ourselves is, how many binary digits do we need? Or another way to say that is, what is the largest power of 2 that is less than that number. In this situation, it was 2 to the 14th, but in general, we actually have a closed form formula to get m, the number of bits. That formula is given by the floor of log base 2 of whatever number we started with, and then we add 1 to the output of that floor function call. After we have that highest power of 2, we subtract away from our original number that highest power to get a remainder, and then we ask ourselves, for each lower power of 2, is that lower power less than the remainder? If it's not, we move down to the next one. If it is, we decompose that remainder into 2 separate pieces, one of which is that next highest power of 2, the other is a second remainder, and then we keep decomposing the remainder until we get all the way down to a power of 2 to the 0. If it is an odd number, that will be 1. If it's an even number, we'll have 0 groups of 2 to the 0. With that, I think we have enough information to actually code up our own decimal to binary conversion that starts with the most significant bit and then moves down. We'll go ahead and use what we call the des2bin_lsb sandbox file. This is going to be a script file that we use to develop the algorithm. In this situation, let's go ahead and set y equal to 19229, since we already have solved that problem. The next thing that we asked ourselves is how many bits are we going to need? We've seen in both this video and previous video that the answer to that question is going to be given by the floor function of log base 2 of our original number, and then we take the output of that floor function and add 1 to it. That gives us the number of bits. We're actually going to encode this binary number using logical data. So we'll call this B, and we'll say that it has all 0 values. How many zeros does it have? Well, it's going to have m of them. So we're going to initialize our binary vector, the binary representation of y, using all logical zeros in row vector form. Before I go on to write any more lines of code, I'm going to go ahead and just test what I have. Notice when I run this, I initialize y to be 19229. That's sitting in memory, and that's actually stored as a double. So if I look at y, we're going to ask ourselves the question, is this a double? And indeed it is. And then also we said that m was the number of binary digits necessary, and I can actually check that using a different mechanism in MATLAB. So if I take the length of the des2bin output given by y, notice that indeed that's 15, which matches my function representation. Then we initialized our binary representation vector to be all logical zeros, where the number of logical zeros is equal to the number of binary digits. In other words, we're going to actually store this using the logical data class, where each entry in our logical row vector is going to represent 1 bit in our binary representation. Now that I know that these 3 lines of code are working, I'm going to move on to the next portion of our algorithm. This is a very good practice in coding. Do not write a ton of lines of code and at the very end close your eyes and push enter and hope nothing breaks. That's not a great strategy. Instead, we write single lines of code or small bits of lines of code, test that that small component is working. As soon as we get that working, we move on to the next one and we build large structures from a sequence of smaller structures. Now let's go over to this representation. Notice what we're going to do is work down from m-1 all the way down to 0, running through all the powers of 2, starting at m-1 and going down to 0. Well, that is a for loop. What for loop is it? Well, I say for index variable I, starting at m-1, going down by -1 and going to 0. Let's go ahead and end our for loop with the appropriate keyword, end. In the loop body, we're going to start with something really easy, which is just take 2 to the power of I and make sure that this loop actually runs through the proper powers that we desire. Let's go ahead and put a pause in this and then test that this works. Notice that the first power is indeed the highest power of 2 that is less. If I continue to just run through this, I just work all the way down to the last power. So indeed, our for loop index is running over the right vector. We can also check that quickly by just checking 14, 13, all the way to 0. Okay, so now the index variable is set to be the proper thing. The next question that I ask myself is the current value of y greater than 2 to the power of the index variable? So specifically, I'm going to ask if the current value of y is greater than or equal to, in fact, 2 to the power of I. Remember, all if statements start with the word if, and then we close those with the word and. So the condition that I'm going to check is the current value of y greater than or equal to 2 to the I. In that situation, the question that we're going to ask ourselves is, let's go ahead and print out that power of y as something that we actually want to produce. So we'll do this by saying, here is the power that we want, and then also 2 to that power. Notice, though, that this is where things get a little interesting, because once I've identified that that power is involved in that representation, I actually need to subtract away from my value of y that power of 2 to get the remainder. And I guess I could do that here. I guess I could just overwrite y with y minus 2 to the I, right? Because what that would say is, okay, if my value of y is greater, then that means there is a factor of this in the linear combination. So in this case, we're actually going to do this really, really easily. We're not going to do any binary representation. We're just going to see, does this pick off the proper power of 2's? I know which ones those should be from this, and so I'm going to print that out in my algorithm. And then I'm going to update the value of y by subtracting away that power of 2. Then I drop out of my for loop back to the index. I decrement the index by 1. I check the next power, which is exactly what we did over here. Let's go ahead and run it. Oops, that was a little bit fast. I didn't pause it. So let's go ahead and pause this, and then we'll go ahead and clear that screen. When I go ahead and run this, the first thing MATLAB does is it sets I equal to m minus 1. Well, m in this situation was 15. 15 minus 1 is 14. So the first value of y in loop iteration 1 is 14. Then I check, is y greater than or equal to 2 to the 14th? 19229 is indeed greater than 2 to the 14th. In this situation, I'm going to print out the vector I comma 2 to the I, which is exactly what I see here, since my logical scalar evaluates as true. Then I'm going to take away from my current value of y the power that I want, which is 2 to the 14th, and that will give me my remainder, which is 2845. Here I'm in the pause condition because I added that as a debugging device. Now I push enter. Once I dropped out of the if statement, MATLAB actually updated the index variable to go from m minus 1 down by 1, so that would be m minus 2. M minus 2 is going to be 13. When we look at the remainder value of y, which was 2845, MATLAB checked, is 2845 greater than or equal to 2 to the 13th? That evaluates as false, so we actually skip the entire body of the if statement. That's why we actually didn't pause for 2 to the 13th or 2 to the 12th, because 2845 is actually not bigger than 2 to the 13th nor 2 to the 12th. It is bigger than 2 to the 11th, which is where we currently are in this iteration. We're paused. MATLAB printed out 11 and 2 to the 11th. Then it takes away from 2845 2 to the 11th, which in this case will be 797. And I can just go ahead and iterate down one by one. And notice the sequence of steps that I get. I get 14, 11, 9, 8, 4, 3, 2, 0, which was the exact sequence that I wanted by my pen and paper analysis. So it looks like this combination of a for loop and an if statement is working properly, is identifying the powers of 2 that I want. The next question is, where do I want to store these powers of 2 in my logical row vector B? One thing that I could try is to store each power of 2 in b to the whatever the power is. So if I were to actually do this, I could say the ith entry of b is going to be true in the situation that y is greater than or equal to 2 to the I. Remember, true is just going to be a logical 1, which is exactly what we've done here. We've translated binary representations into logical truth and false. So here, true, I have 1 to the 14th, 2 to the 13th is false, 2 to the 12th is false, 2 to the 11th is true, false, true, true, false, 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 true, true. Do you see this connection between logical variables and math? Yeah, this is quite deep. Let's go ahead and try this. I already can see that there's going to be a problem, but I want to show you that there's no problem in trying ideas and then breaking your code. Let's run that. Here I'm paused. I'm going to just go ahead and run through by just running, and oh my God. MATLAB is getting mad, and the reason that it's getting mad is right here. This index variable starts at m-1 and goes down to 0. But remember, if I look at b is a logical row vector that starts at 1 and goes up to m. So if I'm going to store the bits in their position values associated with the column index of this variable, I actually need to add 1 to it, since the 0 value of the index corresponds to the 1 value in the column. Before I run that code again, I'm going to take away the pause because I kind of understand what my code is doing at this point. Let's go ahead and run that, and then we'll check at the end. Notice that this value of b is the exact opposite direction of the number that I would expect. So specifically, the number that I want is 1001011001101. But that's the exact opposite, 1011100110101. Those are in reverse order. So one way to fix this is just to set b equal to flip LR of b, and that would actually flip that around, and now I get the exact bit string that I want. But that's not the way that I want to fix it. Specifically, what I want to do is actually work out the indexing variables. So what I want is that my most significant bit, the highest bit, gets stored in column 1. Well, the highest bit is in position m-1. So if I were to say take m away from I, notice when I is 1, m minus m-1 would be m-1 plus 1, which would be 1. When we go down to m-2, this becomes 2. If I go all the way up to 0, that becomes m. That actually gives me the exact representation that I want. When I run this code, I actually get b, which is the exact string that I'm looking for. Now, one problem is that if I were to actually check y to begin with, I've actually run y down to the ground, because every time I'm actually re-updating the value of y, I'm taking away the powers of 2 that I find. I might not want to do this because after my algorithm is over, I actually might want to check the output that I get against the original value. So this is where I might want to use a temporary variable. Let's call it temp. And I'll set that equal to y immediately before my for loop. And then what I'll do is I'll run all of my checks against temp. So I'm going to check temp against the powers of 2. And then if I find a power of 2 that is less than temp, I'll actually subtract away from temp that power of 2 rather than from y. Now, if I clear my memory and I clear my screen and I run again, the nice thing about this is I get the same value of b, but I also have my original value of y out front, which means that I can actually check the values that I have against the corresponding positions. One thing for good measure to really bring home the idea that I am solving the problem that I want to solve, I'll go ahead and set p equal to 2 times, let's call this 1s. How many 1s are there? It's going to be 1 and m of those, so it'll be a row vector. I'll encapsulate that in a pair of parentheses, and then I'll do a component-wise power. Notice that in this row vector, the most significant bit, which is in column 1, that's going to be corresponding to the value of m-1. This is going to go down by 1 and go all the way down to 0. When I run that, I see that that is actually the powers of 2 that I wanted to. Now I'm going to use logical indexing. So now if I take p of b, this will give me the powers of 2 encapsulated by my binary representation. Let's go ahead and push enter. Those are all the powers of 2 in my linear combinations of powers of 2 that make up my original number. And then if I just sum that thing, I should be able to get y back. So let's go ahead and push sum. Indeed, I get that. In other words, this lines 11 and 12 allow me to kind of check that this worked. We can now change this to anything that we'd like to change it. Let's say that I wanted to do something crazy like 25 and then run that thing. Well, we see that the number that I have in my check corresponds with my original flavor, but we might actually want to use MATLAB's desc to bin function as a good check for our own algorithm. In this situation, I'm going to show you something that's a little bit more advanced than beginning students. We have not talked a lot about character data, but This would be a way to achieve a comparable output to the des to bin function. Specifically, if I type bin underscore str, that's going to be binary string, then I'm going to claim that the bit string associated with each of my individual zeros in logical data is a string of 8 zeros. And then for all of my trues, for all of my logical ones, that's going to be 7 zeros followed by a single 1. Well, if I go ahead and look at ASCII encodings of characters, if I add the number 48 to my bit string B, that will shift all of these bit strings up by 48. So the zeros will go to the code 48, the ones will go to code 49, and it just so happens that this is the exact representation as a string, as a character string, of the corresponding binary representation that I want. In other words, if I were to take des to bin of my number y, claim these two numbers are the same, and this gives me a mechanism using my own code to represent some of the functionality that MATLAB's des to bin function does, just in a different way. This last line of code, line 13, is going to be the focus of our community challenge. There's some really special stuff that I haven't covered in any of my videos that is directly related to how we encode characters as strings of bits. Don't worry about that. I'm going to comment out these last few lines of code so that we can focus on the heart of our algorithm. And specifically, we're going to take a look at a flowchart representation of the same algorithm. We start this algorithm by inputting a decimal representation of our desired number. The next thing that we do is we set m to be the number of bits that we're going to need, which is 1 plus the floor of log 2 of y. Then we initialize a row vector with 1 row and m columns of all zeros. In this case, we're using MATLAB's logical data class to do that. We have a long series and, in fact, a good playlist discovering why this is super powerful. Next, I actually went down and I set my temporary variable equal to y so that as I did algebra or arithmetic on my temporary variable, I actually stored the original value. If I write this as a function rather than a script file, I might not actually go that far because of what we call global versus local variables. But because this is a script file, I'm going to actually use that temp variable as associated. This is where we dropped into the for loop, and our for loop allowed us to check all powers of 2 starting at m-1 and going down to 0. So we initialized the for loop index at m-1. And then each time our for loop each time we're about to enter our for loop, we make a simple check. Do we have powers of 2 left to be checked? In other words, is our index greater than or equal to 0? If that is false, if we've checked all powers of 2, we exit our for loop and we continue with our program. However, if it's true, we drop into the body of the for loop, and then we're going to check the following condition. Let's take a look at our temporary variable and figure out if it's greater than or equal to the power of 2 to the current value of the index, because that's literally what we were doing in the work over here. Each time we dropped down to the next remainder, we took the highest power of 2 that we could that was less than the corresponding remainder. Once we did that, we broke it into 2 pieces, that power of 2 and everything remaining, which is what's happening here. The moment that we notice that our power of 2 does show up, we are going to set one of the bits equal to 0. The question was, which bit are we going to do? In my case, I wanted this to have the most significant bit on the left-hand side and the least significant bit on the right-hand side. So I did some math on the indices to make that happen. We also saw in this video a way to switch those, little endian versus big endian. That's kind of a fun topic. This idea of figuring out where the indices goes is one of the pleasures and pain of array-based thinking, and we'll see a lot more of that in this class. In our case, we use logical true everywhere where that power of 2 shows up, which is what we see. And then once we've accounted for that power of 2, we take it away and find the remainder, overwrite the value of temp with that remainder, update the for loop index, and then we check, is there any power of 2 left? If there's not, we drop out of the for loop. If there is, we check, does the next power of 2 belong in my representation? If it doesn't, we just update. If it does, we drop in. Once we've repeated that m number of times, starting at m-1 going down to 0, we drop out of our for loop, we produce our binary representation, and we end. As promised, that leads very nicely into our community challenge in this video. In the comment section below, please describe what the hell is happening with this line of code. Why does this work? We saw that this actually produces a character string that is identical in the test case that we have to the output of des to bin. My question is, why does it work? How does this work? Write that answer in the comment section below. I will end this with the conclusion: we now are turning math problems into logical problems, and this is very powerful because we can implement logic using electronics. That is the core idea, literally the central idea inside the computers that we're using right now, is that we implement logic using electric signals. And what we've done in this video is actually show how to turn numbers into logical data. Welcome, my friends. We are starting to get sophisticated. Woohoo! As always, I welcome your comments, questions, concerns in the comment section below. When you give me feedback, I become a better content creator. Thank you so much for your attention, and I'll see you in the next video where we see a different algorithm to convert decimal to binary. See you there.